talk a little bit about some science, and in particular here in Vilnius, what we are doing, we are modeling the molecular properties of of mainly liquid phase materials by using quantum mechanics, quantum chemistry-based methods, as well as molecular dynamics simulations. So in particular, we are interested in the molecular properties of large molecular systems. And you very well know that if you are interested in the electronic molecular properties, then you need to use quantum mechanics-based approaches. And these are pretty expensive. And due to their high scaling, even DFT, density functional theory methods, they scale as n to the power 4, or maybe if it's a good implementation, it could be reduced to possibly n to the quadratic scaling with respect to the number of basis functions. Still, these methods are rather expensive. Well, if we want to study large molecular systems, and by large I mean something like for example, a molecule solvated in some liquid, or perhaps if you have a molecule bound at an active site of some protein, then the raw quantum mechanical methods, quantum chemical methods, they will not work, and then you need to do some tricks. So here we are using what is called the combined quantum mechanics, molecular mechanics models. And the idea behind these models is to take your large molecular system and subdivide it into two parts. Usually the part which you are interested in, the properties of which are of interest, this part is usually quite small. Like, for example, we have a molecule solvated in some liquid. Here it is water. Then we possibly are only interested in the properties of the solute, whereas we can look at the solvent as being of secondary importance. So therefore, we use this QMMM model, which only uses the precise and we could say accurate quantum mechanical description for the small part of the system, whereas the rest of the system is described by molecular mechanical potential. So basically, this is a classical description of the environment that the solute or the molecule of interest is around. Is founding itself within. So why are these models good? First of all, this model still allows preserving the discrete nature of the solvent molecules, or perhaps of the environment, if that environment is a protein. And this is in contrast to these very well-known dielectric continuum approaches, which treat the environment as a homogeneous dielectric medium. And in this kind of approach, of course, all the discrete nature of the molecules is neglected completely, because basically the environment is represented by glass, if you like, something like this. So one of the issues then related to using the quantum mechanical, molecular mechanical models is related to statistics. And first of all, if you have here a system like this, that you have a solute in some, and you have a lot of solvent molecules around them, then the question arises, how do you distribute these solvent molecules around the solute? And it's quite clear that there are so many ways that this can be done. And many of these different configurations, different molecular configurations will have a comparable energy, meaning that obviously we need to involve some kind of statistics. And this is where molecular dynamic simulations come in. But I will talk a little bit about this just a little bit later. So if I may now, I would like just to tell a little bit more about the details of the QMMM model. So again here, if we have this partitioning of the molecular system into what we refer to as QM part, here and the part, then this also implies that the Hamiltonian of the system is likewise partitioned in the following manner here. So here we have the Hamiltonian, which is a purely quantum mechanical Hamiltonian in vacuum. And this is the usual quantum mechanical Hamiltonian of the molecular system or of a molecule within the Born-Oppenheimer approximation. Then we have this other part, which is represented here, this HMM. That's the part of the Hamiltonian which describes the intermolecular interactions of the molecules in this classical system, or this MM subsystem, if you like. And now the important part, the all-important part, is this HQMMM, and this Hamiltonian, this part of the Hamiltonian describes how the two systems talk to each other. I mean, how the quantum mechanical system talks to the classical system. And this can be realized, this interaction between the systems can be realized in several ways. The simplest way is to take simply the point charge distribution and represent the classical molecule simply by this point charge distribution. You can go a step further. You might not only assign the partial point charges, but you can also assign higher order static multiple moments like static dipoles and static quadrupoles. I think the implementation we are using is able to treat multiples up to octupoles in some instances. So still, wherever you truncate this expansion, this multiple expansion here, still these multiples will generate a static inhomogeneous electrostatic potential, which is felt by the electrons of the quantum mechanical system. So in this way, the classical system polarizes the quantum mechanical system. And these methods are called the electrostatic embedding. We might also meet that term like this. But then we can also still make another step forward by assigning not only the static multiple moments to the molecules in the classical part, but also dipole-dipole polarizabilities. These can be either isotropic polarizabilities, or you can also use the tensor form. I mean, how they should be. I mean, as a second rank tensor, that these polarizabilities are represented mathematically. So now that you have these dipole polarizabilities, then these give rise to the induced dipole moments in the classical system. And now new physics comes about because the magnitude, I mean, the values of these induced dipole moments will also depend on the electronic density of the quantum mechanical system. And vice versa, the dipoles will also affect charge distribution in the quantum mechanical system. So we gain now by such an approach is the mutual polarization between the quantum mechanical and the classical system. So this in this way we introduce the many-body effect. Now, in order to arrive at the practical computational scheme, then
I'm sorry, Kestutis, time to time the sound became not so clear. Maybe something with microphone.
Okay, can you hear me now?
Now it's perfect.
Now it's okay. Okay, I'll try. Please let me know if problems arise again. So. So if I should take a few steps back, when did you stop hearing me? Okay.
No, it is not necessary to go back.
Okay.
In Zoom, it was okay every time. Thank you. It was okay.
Okay, I see. Thank you very much. Okay, so let's continue here. So this is what we have been talking here. Here is the theoretical scheme of QMMM model, but we want to arrive at a practical scheme that we can actually utilize this model in a computer, in a quantum chemical problem. So what one does is, if we take a then Hartree-Fock equations, which are integral differential equations, they are transformed to the matrix equations, which are called Roth and Hall equations. So you arrive at the Fock matrix, which then eventually has to be diagonalized in order to solve the Roth and Hall equations. If we consider the Hartree-Fock approximation for the quantum mechanical part of this model, then the scheme works very much similarly like in vacuum. Just additional contribution to the Fock matrix arises, which simply has to be added to the otherwise vacuum Fock matrix. And then you continue with the SCF procedure to diagonalize these Fock matrix and solve your Roth and Hall equation. Should this be a polarizable QMMM model, meaning that polarizable centers have been assigned to the classical molecules, then an additional procedure arises, because in every iteration of the SCF procedure, these induced dipole moments have to be calculated. And they can be calculated either iteratively or by the matrix inversion techniques as shown in this equation here. But nevertheless, it's not a very expensive step. And still, the good thing about the QMMM model is that only the one electron contribution arises that needs to be calculated in order to calculate this QMMM contribution to the Fock matrix. So you only need the electric multiple integrals as well as electric field integrals, and these are the one electron integrals, so they are not that expensive to calculate. So the QMMM calculation is just a little bit more expensive than compared to just simply a vacuum calculation for the isolated. Okay, so now, as we have been mentioning, we need to combine the QMMM methods together with some statistics. We need to involve mechanics in a way. And the way we do it in our group, we are relying on the classical molecular dynamics simulations. So this is another family of molecular modeling methods, but you very well know these methods, so I will not talk much about them, but I would like maybe just to highlight a few points which are important in relation to the classical molecular dynamics simulation. So you very well know that this is an empirical method, so that the interactions between molecules are described by the empirical force field or empirical potential, which involves a bunch of parameters. So these parameters have to somehow be developed, and where this is going is that it is good to have force fields which are specific to the problem you are solving, to the molecular system which you are trying to simulate. And this is maybe not that crucial for the ordinary systems like traditional solvents, traditional organic molecules. But when it comes to a little bit more modern materials, which are not that traditional, then you need to use these specific force fields, and I will mention a little bit about this later. Okay. Now, then what we normally do, we run. It is important to reach the statistical equilibrium of the system that you are simulating, and then we do it in several steps. We first use simulations in the NPT ensemble, meaning that we wait until the density of the system is equilibrated, and then we switch normally to the NVT ensemble. And we run the production run of the simulation takes, well, whatever, how long it needs to be. And then we sample the trajectory of the molecular system. And this trajectory is used in two ways usually here that we do in our in our group. So first of all, this of course provides.
Меня пустило.
We analyze our trajectory.
Я не знаю, Жек. Алло.
Excuse me. Yeah.
This is somebody.
Okay. So we
Yeah, please continue.
Okay. So what we do, we analyze the trajectory to gather this radial distribution, coordination, other related structure. We also are sometimes interested in the dynamical properties like diffusion coefficients, and these can be calculated from the molecular dynamics as well. I will show an example of this as well later. So, and the second purpose of sampling the trajectory is to use in relation to the QMMM calculations. So what we do, take a reduced set of molecular configurations, and we apply the QMMM model for every configuration in this set. So before we do the QMMM calculations, there are still a few points which need to be considered. Of course, that's the choice of the electronic structure method for whatever properties you are trying to calculate. And we here normally rely on the functional theory methods, as it's popular, of course, nowadays. So then, of course, there is selection of the one electron basis well. So normally some kind of basis set analysis is needed to be performed, especially if you are trying to consider new molecular systems and maybe new properties, new properties to be calculated. And then there is this partitioning of the entire system into the QM part and the MM part. So the simplest approach is, of course, to treat only the solute molecule quantum mechanically, whereas the environment, the entire environment could be treated using this molecular mechanical potential, maybe the point charge distribution. But it is also possible to expand the quantum mechanical system by including some of the solvent molecules which are close to the solute. And this is normally needed, especially if there are hydrogen bonding interactions formed between the solute and the solvent, but also other types of interactions, maybe pi-pi stacking could be important as well. And here we actually are interested in the nuclear magnetic resonance spectra of our materials, which we are studying. And usually we do this proton NMR. So as the protons are normally situated at the outer region of the molecule, it's in the exterior of the molecule, then protons are directly feeling solvent molecules. And what we have seen is that it is in fact needed to expand the quantum mechanical region to include the entire first solvation shell of the central molecule in order to arrive at the reliable results for the NMR chemical shifts. So finally, once we have done this bunch of calculations, QMMM calculations on the molecular configurations from the MD simulation trajectory, then we go in and we do the averaging of those properties, for example, of the NMR chemical shifts. And this is how we arrive at the liquid phase results, which can be now compared to experimental data and be analyzed in some other way. So let me now maybe move to some examples, recent examples of applying this computational scheme. So over the last few years, we have been very much interested into the properties of this material called ionic liquids. So these are really fascinating materials because they are composed solely out of ions. So there is a cationic part and there is an anionic part. But unlike conventional salts, ionic liquids, just as the name tells, they are liquid. Usually, they are liquid at the room temperature, and from this, I mean, they have very interesting properties because they are made out of ions. Then they do not evaporate at room temperature, even if they are in liquid phase, in the liquid state. And they have other properties. They are conductive to the electricity, and they have found many applications in different areas so far. So they can be used as electrolytes in electrochemical devices. They can be used to purify water from contamination with heavy metals. They could be used in biochemical applications. For example, they can be used as media to preserve the native structure and function of proteins for very much prolonged times as compared to the ordinary buffer solutions, for example. They can also be used in pharmaceutical sciences. They can be used as drug delivery vehicles. They can be used as hydrotrophs, which simply work in a way that they enhance the solubility of otherwise water insoluble or poorly soluble drug candidates, or maybe old drugs. So there are really plenty of applications, and these materials are still being actively studied. Here on the right, you can see just a little part of different cations and different anions that can be combined into ionic liquids. And in principle, there are myriads of different ionic liquids that can be synthesized. But so far, maybe just, I think it's maybe just over 500 or 600 different ionic liquids are available commercially, and maybe just above 1,000 different ionic liquids have been documented in the scientific literature. So it's not that it's myriad in practice, but still on paper that can be done. So now, if we want to understand how these ionic liquids work, then it is it's of utmost importance to really study these materials on the molecular level. So this is what we try to do. We have tried to look at the molecular structure of ionic liquids, and also especially of their solutions or their mixtures with water, because very often ionic liquids are used in combination with other solvents. And the reason being is that these materials are, even though they are liquid, but they're normally very viscous, and they are at least 10 times or maybe hundreds of times more viscous than water at ambient conditions. So it makes sense to actually mix them with water so that the viscosity is reduced, but these properties of ionic liquids are still preserved. So it's a typical that ionic liquids are used in relation or in combination with water. Now, in biochemical applications, of course, water is the integral part of any life-related system, so that cannot be avoided. And further, it is also very difficult to purify ionic liquids. They are usually very hygroscopic, so it's a pain, really, it's a pain to get, and it's also very expensive to get pure ionic liquids. So it's really a good thing that they can be used as mixtures with water. So what we have been trying to do, we have here an NMR laboratory next door, so we collaborate with them very much, and we are using the computational nuclear magnetic resonance spectroscopy to characterize different aqueous solutions or aqueous mixtures of these ionic liquids. And I would like to in particular highlight the family of imidazolium ionic liquids. This is by far the most studied family of ionic liquids. And here I would like to show you, here on the left, you can see again the most popular imidazolium cation, which is normally used for synthesizing ionic liquids, which is 1-butyl-3-methyl imidazolium cation. And here you can see a very typical NMR spectrum, the proton NMR spectrum of this imidazolium cation. So whichever, no matter which anion you use to combine in order to form the ionic liquid, this NMR spectrum of the imidazolium cation will look basically the same. But here there is the signal of the proton at the second position, so at this position over here. And this signal is pretty special because this CH group, the carbon-hydrogen bond here, is quite acidic. And it is very much involved in hydrogen bonding interactions with whatever approaches this imidazolium ring from this side. So these are usually the anions in the ionic liquid, but it could also be water molecules if we have mixtures with water. So the chemical shift of this proton at the second position turns out to be very sensitive to the structure and the nature of the environment close to this imidazolium ring. So in this way, we can use the chemical shift of the proton at the second position as a structural probe of its immediate environment. So this is nice. And then earlier, some years ago, we tried to model the proton NMR spectrum of this ionic liquid, 1-methyl-3-butyl imidazolium chloride of the neat ionic liquid. And we used our computational technique just as described. So we performed the molecular dynamic simulations of this ionic liquid, and we used the QMMM model to calculate the proton NMR spectrum of this imidazolium ion. And again, these were pretty hefty calculations because we had to include the entire first solvation shell of the central imidazolium cation into the QM part in order to get the reliable results for the isotropic shielding constants of protons of this imidazolium cation. Now, it might come as a surprise, but the rest of the system, so all these ions in the second solvation shell and beyond that, they turn out to be almost irrelevant. So for the proton NMR data, it's only really the molecules in the immediate vicinity of the cation that mainly determine the values of the proton chemical shift. So here on the right, you see the comparison. Here on the right, you see the comparison between the measured spectrum and the computed spectrum. So this red line serves as a unit line and it aids the comparison. So if you have these points on the line, that means that the agreement between theoretical calculations and experimental data is good. And you can see this is mostly the case, with the exception of the chemical shift of the proton at the second position. You can see that our computations have underestimated the chemical shift of the proton at the second position, and quite severely. I mean, we have made an error of 1.4 parts per million, and this is a large error. I mean, for the proton NMR data, this is a large error. So this is not a very satisfactory result, but it is very well known actually that it's not easy to calculate the proton NMR spectra of imidazolium ionic liquids accurately. So here, more recently, we actually succeeded in predicting the entire proton NMR spectrum of another ionic liquid, which is the same imidazolium cation, but with another an ion combined with another anion, that's with tetrafluoroborate, another very popular ionic liquid. And we succeeded not only predicting the proton NMR spectrum accurately for the neat ionic liquid, but also for its aqueous mixtures. So now this ionic liquid is a little bit special in a way that if you scan the chemical shift of the proton at the second position by changing the composition of the aqueous mixture of the ionic, then this chemical shift at the second position turns out to be basically insensitive to the molar fractions of water and the ionic liquid in the mixture. And this is a very special case for this ionic liquid, because if you take any other ionic liquid with the same cation and another anion, then the chemical shift of the proton is very sensitive to the composition of the mixture. But for this ionic liquid, for some reason, it is not. And it has been speculated in the literature. I mean, not speculated really, but the conclusion comes from the experimental work that unlike for other ionic liquids, the tetrafluoroborate anion is positioned on top and below the imidazolium ring, meaning that you don't have this linear hydrogen bond between the C2H2 moiety and the anion. And simply then, apparently, if you change the composition of the mixture, this doesn't affect the chemical shift of the proton at the second position very much. So what we have done, we also performed the structural analysis, and we have seen that this is not really the case. The tetrafluoroborate is situated not really in the plane of the imidazolium ring, lying more or less linear geometry of the hydrogen bond, but it's situated somehow in between, not really on top, but at an angle, and that's the conclusion that comes from our molecular dynamics simulations. So we have done the structural analysis here, and you can see that here on the left, we show the coordination numbers of water molecules and also of tetrafluoroborate anions around this proton at the second position. So in the beginning, going from the neat ionic liquid to the mixture with 50-50%, you see that the coordination numbers of the ions are not changing that much, but then if we go to the 17% system, then the coordination numbers dropped a little bit more. And also, the more water you have in the system, the higher are the coordination numbers. But the good thing, or the thing that I would like to highlight is, of course, this figure here. We show the comparison between the experimental and computed NMR spectrum for the imidazolium cation in all four systems. And you can see here that even the chemical shift of proton at the second position was predicted really accurately here. So we somehow arrived at this very satisfactory agreement for the entire proton NMR spectrum of this ionic liquid and the aqueous mixture. So that's pretty nice. So another study which I would like to show you, I can see I'm a bit running out of time here. So yes, maybe let me skip this one, even though this is interesting, but let me also show you another study we have recently done. It's now we are not so much interested into the properties of the ionic liquid itself, but we rather put something inside the aqueous mixture of an ionic liquid, And this something is a drug molecule, which is called glibenclamide. It's an anti-diabetic drug, and it's an old drug. It's known for a long time. However, its applications, so practical applications, are somehow limited due to its very pure aqueous solubility. But then here, maybe 10 years ago or so, it was shown that if you use this ionic liquid, the choline tryptophanate, as shown here, if you put a little bit of this ionic liquid into water, then this ionic liquid acts as a hydrotrope towards the solubilization of vancomycin. So if you have a mixture of choline tryptophanate with water where the molar part of the ionic liquid reaches, I think it was 10%, then the solubility of glibenclamide rises by around 600 times. So this is a significant increase in aqueous solubility of this particular drug. Now, this is another family of ionic liquids. These are bioactive ionic liquids. As you see, the cations are here. These choline cations, they are biomolecules. They have a biological function, and they also are a part of the membranes of the cells, and then the tryptophanate line, that's of course one of the natural amino acids. This is a third generation ionic liquid, the choline ionic liquids, which are combined with the natural amino acid-based anions. So this is another very actively studied family of ionic liquids. And because they are composed solely out of biomolecules, it is hoped that they can be used in biomedical applications as well, unlike the imidazolium ionic liquids, which are, even though they have been termed green chemicals, I mean green materials, but they are there for the human body, for life in general. So what we would like, what we were willing to do in this study, we were willing to really look at this molecular mechanism behind the hydrotropic action of choline tryptophanate towards the solubilization of glibenclamide. And there are several hypotheses, if I may say, proposed in the literature towards, to explain the hydrotropic action of materials. And one of them is related to the formation of small molecular aggregates between the solute and the hydrotrope molecules. And that should somehow drive the hydrotropism of the hydrotrope, so to say. So if that is the case, then we thought that the NMR spectrum of glibenclamide should be sensitive to the formation of these kind of molecular complexes. So we asked our NMR people to measure the proton NMR spectra of glibenclamide dissolved in water and dissolved in the aqueous mixture of choline tryptophanate, and see if there are differences between these spectra. And I have to admit, for me, it was almost hopeless, because due to this very pure solubility of glibenclamide in water, and NMR, you very well know, it's not a sensitive method. I thought they won't be able to see the spectrum in pure water, but they were able to do it. It's admittedly not in normal water, but in heavy water, but still in water. So we are very proud that they were able to measure the NMR spectrum of glibenclamide of pure dissolved in heavy water. So this is spectrum on the bottom here, and then they also measured the spectrum of glibenclamide in this aqueous mixture of choline tryptophanate. And it's maybe difficult to see here, but there are really differences here. The entire spectrum in ionic liquid is shifted towards towards in one direction. I think it's to the larger, no, to the smaller values of chemical shifts, but it's not a uniform shift. Subsignals shift more, others shift less. So it's really true. The NMR spectrum is sensitive to the presence of the ionic liquid in the system. So we wanted to study this. We have carried out molecular dynamics simulations. We studied the conformational equilibrium of glibenclamide in both water, in aqueous solution, and in this mixture of the ionic liquid and water. And we saw some differences. So in water, the glibenclamide being a hydrophobic molecule, it somehow more frequently adopts like U-shaped or S-shaped conformations so that the surface accessible to polar water molecules is reduced. However, if you put glibenclamide in the aqueous ionic liquid mixture, then the population of this extended conformation of glibenclamide rises. So that that's what we've seen. And we have also seen the condensation of the ions of choline tryptophanate around glibenclamide molecule, as shown here by these radial distribution functions. We will not go into details, but let me just mention that it is especially the anions that are condensing around glibenclamide molecule. And now tryptophanate, it has the pi electron system, it has these two fused rings, and also there are two benzene rings in the glibenclamide molecules. We have also found that there are prominent pi-pi stacking interactions formed between tryptophanate anions and the benzene ring, this particular one of the glibenclamide. So really these complexes between glibenclamide molecule and the ions of the ionic liquid are truly formed. This is what we see in from our molecular dynamic simulations. And here you can see the coordination numbers around the three rings of glibenclamide. So you can see that in particular, the tryptophanate ions, they show high proclivity to condense around glibenclamide. So now, is this really, I mean, this is the MD simulation. So what we use is the computational NMR data in order to confirm that this might really be the case. So what we did, we calculated the NMR spectra of glibenclamide in aqueous solution and in this ionic liquid and in the mixture of the ionic liquid and water. So here is the comparison. Again, without going into details, maybe this figure is of interest. So here we show how the individual NMR signals from protons in glibenclamide change from going to from aqueous solution to the aqueous ionic liquid solution. And you can see that qualitatively the comparison is exactly as it should be. You see that all chemical shifts are reduced in magnitude. I mean, the absolute, the quantitative agreement is not always that good, but maybe, well, having this model also have some limitations. So still, we are very happy with the qualitative result that we have here. So we really see in this way, our study somehow confirms, I mean, somehow supports this hypothesis of the formation of small molecular aggregates of the solute and of the hydrotropic molecules. So that now hydrotropic molecules, they screen the hydrophobic solute from the polar water molecules. And this maybe is the driving force. This could be a driving force behind the hydrotropic action of ionic liquids and maybe other type of materials. So my time is running out, so I would like to to finish with some acknowledgements. So first of all, again, thank you for my team of young researchers and PhD students I am honored to work with. I mean, without them, these results would not exist. I have some extensive collaborations here in Lithuania and abroad, and thanks to these people as well. Of course, thanks to the Lithuanian Research Council for support, to the POSI action that Professor Litz and myself we are part of, and it's always a pleasure when our paths cross. And I would also like to thank you for your kind interest in the Thank you very much.
Thank you very much. Let's thank our lecturers. Okay, now we have a time for questions. Please, questions in our room, maybe in Zoom. Yes, we have a question in our room. So this Iris on.
Yes, thank you very much for this very nice lecture. Maybe I would have some technical questions. So, for example, which exchange correlation do you use in the DFT part? DFT, and the second is, do you have problems with the conversions of the basis set in the NMR shift? Because usually one has to use very specific. So, which kind of basis set do you have?
Thank you very much. Yes, your questions are exactly to the point. I mean, it's a crucial thing of selecting the electronic structure approach in these QMMM calculation, as in any type of quantum chemical calculations, really. And so we have been studying this NMR properties for quite some time, and we have over the years used several DFT functionals, and that's first of all involves this PBE0 functional, which turns out it's quite good for the NMR property. It has been benchmarked extensively, and it was the conclusion of several independent studies that the PBE0 functional is good for calculating NMR isotropic shield for chemical shifts. We have also been using these Kiel and Tozer family of functionals, which have been specifically designed to provide reliable results for the NMR shielding constant. So in several instances, we have used that one. But in these studies, lately, we have really settled on the PBE0. So I know this is not the most modern functional, but whenever we try, especially with the students here, to make our little study maybe benchmarking against a couple cluster approaches, if that is possible, then we end up with the same conclusion. The PBE0 from all those functionals we tried somehow gives the best result for the chemical shifts. Now, in relation to the basis set, you are absolutely right. The isotropic shielding constants is a painful property to calculate as long as basis convergence is concerned. But the good thing is that we don't really need the isotropic shielding constant, but what we need is the chemical shifts. And the chemical shifts are differences in the isotropic shielding constant. Now, it's just a luck, but when you calculate the difference between the two isotropic shielding constants, calculated using the same level of theory, these errors tend to cancel. And the chemical shifts turn out to be very well comparable to the experimental data. I mean, how good is this error cancellation? That you never know. I mean, yes, but it's really a good thing of computational NMR that these chemical shifts come as differences in isotropic shielding constant, and then you can rely on error cancellation. Because otherwise, you would be needing to really use large bases involving size war functions and possibly even diffuse functions. That would be a painful exercise to do. But due to this error cancellation, normally moderate sized bases that are okay. And here we normally use the Ulrich's family of bases. Bases like second definition or second generation of these PZBT bases. They work pretty well for the NMR spectrum in our.
Thank you very much. If there is no question, I would like to ask a question about that part which is related to the molecular dynamics of last part, molecular dynamics, where you observe condensation of anions on complex.
Yes.
I would like to understand why it happens, because of course you have electrostatic charge, but if we look at the radial distribution function, the next slide. Yes, so as I see this large peak, the first peak,
exactly
indicates this condensation. And what is the charge of the complex?
Yes. So the benclamide itself, it's a sulfonamide type of drug. So the sulfonamide moiety has a small pK. It's an acidic moiety. So at normal pH, it deprotonates. So it's an anion. The molecule itself is an anion, and this negative charge is located mainly at this sulfonamide moiety like this. It's not very well shown, maybe here. So this is very and now so that's one of the reasons. But but you are completely right. It's a bit curious. The molecule itself is an anion, and the sulfonate is an anion. They still somehow end up interacting. And it's not only electrostatics that drives this interaction. Of course, these are the van der Waals type of interaction as well. So in particular, we have this flat benzene ring over here, and we have this
Сидела на балконе.
Так вот тогда мог тоже залететь.
This pi-electron system here, and they somehow form the pi stacking interaction. So here we have this figure. So what we have done, we performed a statistical analysis of the distribution of an angle between the planes of the benzene ring here of tryptophanate and the benzene ring of the benzene ring of the benclamide and the benzene ring of tryptophanate at the cosine of that angle, and how is it distributed with the distance between the centers of mass of these rings.
So this is due to the pi stacking.
Exactly. Yeah. So you see these red spots here. They indicate that we have an increased distribution of these two rings being very close to each other. So in the pi-stacked configuration. So this is one of the specific intermolecular interactions that drives the this condensation of the anions around the glibenclamide. But another interesting thing is that even though there are possibilities for hydrogen bonding between the ions of the ionic liquid and glibenclamide, we basically didn't see any. For some reason, the hydrogen bonding is not very abundant in these systems, which was kind of a bit the contrary to our expectations when we.
Okay. Thank you very much, dear colleagues. Other questions? In our room, there is no questions. Maybe